Okay, in calculus, we've talked about derivatives and integrals. Those are the two basic things we talk about. So this topic combines both derivatives and integrals. And what we're going to be studying is slope field. So a slope field is just made up all these little line segments that have a slope, or it's called a directional field. And if you take a function and imagine at every part of that function just drawing a small tangent line, that's where a slope field comes from. So I'm going to show you a few different examples to show you how you'll use it here in calculus. So this is a slope field for the function dy dx equals x. What that means is the slope of that function is equal to x. So it's actually kind of very boring to look at. If I make a t-chart and label one column x and one column dy dx, what I would find is, well, if x is 0, my slope is 0. So what you would do is you would draw these little line segments with a slope of 0 everywhere x is 0. When x is 1, my slope is 1. So everywhere x is 1, I draw a little line segment that has a slope of 1. Likewise for 2. So it's a little steeper, and I'm not going to do the whole thing. 3. So on the other side, -1, you'd have a negative slope. And you would generate this whole slope field. So we could find a solution to a differential equation. So my solution would be to solve for y. So to rewrite this, I would rewrite dy equals x dx. And then I would go ahead and integrate both sides of the equation. If I integrate dy, I get y. If I integrate x dx, I get 1/2 x squared. And I have to have a constant. This is the general solution. That means that this slope field would work for any function y equals 1/2 x squared plus c. So if I move this up, grab another color. If I move this up, if c were 1, it would look like this. If c were -3, it would come down 3, and it looks like this. So that's the general solution. If I want to find the particular solution, I would have to use this initial condition that they've given me. So I'm going to use the point 0, 0. So 0 equals y, 0 equals x, and I would solve for c. That's actually a really boring one, c equals 0. So my particular solution would be y equals 1/2 x squared. And I could show you a lot more examples with this. I just really want you to get the start of the understanding of this. Here's some slope fields that are already completed, but I'll show you how to start picking out characteristics of a slope field to match it to an equation. So I've got this function dy dx equals 2y. So if I make a t-chart, all I have are my variables y and dy dx. Well, similar to the last one, I'm going to start putting a value for y. I like to put 0 for y. If I put a 0 for y, 2 times 0 is 0. So anytime y is equal to 0, that's where they get those slope fields there. That slope of the segments. If y is equal to 1, 2 times 1 is 2. So anywhere y is equal to 1, all these are 1, I have a slope of 2. anytime y is equal to 2. 2 times 2 is 4. So I've got, it's a little steeper. It goes like that. And then -1 gives me -2. -2 gives me -4. And that's where they got all these values. So once again, not real exciting. The first one only had x. This one only had y. The next example I'm going to show you has x and y. Well, actually, I want to go back. I wanted to show you something here. If I want to find the general solution, I would take dy dx equals 2y. I would separate this out. So I'd have dy divided by y equals 2dx. So I'm just going to head into divide by y and multiply by dx. So now when I integrate this, when I integrate dy over y, it's the same thing saying if I integrate 1 over u prime, or I think we've been using du, as equal to the natural log of u, absolute value of u. So this side is going to be the natural log, absolute value of y. When I integrate this side, I get 2x and then plus c. And then there is a way to solve that for y, which I'm not going to do today. We'll do it at a later time. So now let's go on to this slope field here. Now I like this one because it has x's and y's, and then you get to see a little bit better what's happening. So I'm going to make it, I can't really call it a t-chart now because I'm going to have 3 columns. I have x, y, and I have dy dx. So there's patterns, and if you recognize patterns, it makes it a lot easier. So if I put a 0 for x, it doesn't matter what y is because I'm going to have a 0 in the denominator, and dy dx is undefined. So that means I have a vertical tangent line. So anywhere x is equal to 0, so right here, those are all vertical tangent lines. Anywhere y is equal to 0, so 0 over x is always going to equal 0. So that's where they're getting these tangent lines. And now I could pick some different points. Let's look at this point 1, 1. If x is 1 and y is 1, I have -1 over 1, so I have -1. So the slope is -1. Let's pick this point here, 3, 1. So that's going to give me -1/3. So it's a negative slope, but it's not as steep as this one. And let's do another one. Let's do -2, -1. So I'd have -1 over -2. So it gives me -1/2. So I would think -1 this way. I'm just going to go a little less steep. And that's how a slope field is done. And I've only chosen some of the key points and a couple other points. If I wanted to solve this one, I would get the y's on one side, so I have dy over y equals -dx over x. Integrate both sides. I'm just going to keep the negative on the outside. When I integrate dy over y, I get natural log absolute value of y equals natural log absolute value of x plus c. And that's my general solution. And like I said, later on, I'll teach you how to solve that for y. Here's a question from the 2005 AP test on slope fields, and slope fields were fairly new to AP Calculus on the AB version at this time. It's been on the BC portion for a long time. So, and I'm not going to go through the whole problem on this. I'll leave it for another day, but I just kind of want to show you how you could see it. So first of all, I have this differential equation right here. And it's giving me initial condition, and that would help me find the particular solution. So let's first look at what we need to do. It says, on the axis provided, sketch a slope field for the given differential equation at the 12 points. So they actually have marked these points that they want you to work on. So I'm going to do a chart, but I'm going to look for patterns. Because if I don't look for patterns, it's going to take me too long. So kind of like the last one now. If x is 0, no matter what y is, I'm going to get a slope of 0. So x is 0 here, here, and here. No matter what x is, when y is 0, my slope is 0. So I'm going to get this one, and this one. Now I only have 6 points left to do. So I have the point -1, 1, -1, 2, 1, 1, 1, 2, 2, 1, and 2, 2. So it's still going to take me some time to do this, but not that bad. So -1 and 1 squared over 2. This is going to give me a positive 1/2. So at the point -1, 1, I make sure I have positive. This would be positive 1. I would just slope it down a little bit and do 1/2. -1, 2. So I have -1, 2 squared over 2 gives me a positive 2. So at this point, oh, actually I did that in the wrong spot. That's why I have an erasable pen. 1/2. So -1, 2 gives me a positive 2. 1, 1, negative, put a 1 here, put a 1 here, over 2, gives me -1/2. So at the point 1, 1, I'm glad I caught that. It's not negative, or it's not a positive 1/2. This is -1. I'm going to do it like that. And I've got the rest of these done. So -2, -1, -4. So at the point 1, 2, I have a slope of -1. At the point 2, 1, I have the point -1. And at the point 2, 2, I have -4. So that's what the slope field looks like. And I don't want to take the time today, but the next question asks you to write an equation for the tangent line to the graph of f of x equals -1. So to write a tangent line, you would need a point and you would need a slope. Well, we have the slope, that's at dy dx. So we would need a point. So the next part is you want to find the solution with the initial condition f of -1 equals 2. So that means you'd have the point -1, 2. Well, that one works. -1, 2, I can actually use that as this point, and I've got the slope and I can find it that way. And then I would find the general solution, and then that would be differentiating it. And this one's a little bit more complicated. I'll leave that one for another day. I think slope fields are fun. I hope you find them to be interesting and fun as well.